Welcome to our channel, fellow explorers of the cosmos. Today, we're zooming down past the atoms to the very heart of matter, the nucleus. This tiny realm holds the secrets to some of the most powerful forces in the universe. By the end of this video, you'll be able to explain these concepts to anyone with ease. So buckle up, get ready for some mind-blowing science, and let's unlock the mysteries of nuclei together. Alright, let's start with the big guy himself, Albert Einstein. You've probably heard of his famous equation, E = mc2. It's the key to understanding the fundamental connection between mass and energy. Mass and energy are actually two sides of the same coin. They can be converted into each other. Think of it like this: mass is like energy taking a nap all bundled up. But when that energy wakes up, watch out. Every time you light a match or cook food on a gas stove, you're witnessing this principle in action. It's happening on a much grander scale in the sun, where nuclear fusion is constantly converting mass into energy. So that warm, sunny day, you can thank E = mc2 for that. Now, let's talk about the nucleus itself. It's made up of protons and neutrons, right? But here's the thing. The mass of a nucleus is actually slightly less than the sum of the masses of its individual protons and neutrons. This difference is what we call the mass defect. Think of it like baking a cake. You've got your flour, sugar, eggs. All those ingredients have their own individual weights. But when you mix them together and bake the cake, some of that weight seems to disappear. The missing mass in the mass defect is actually converted into energy, the binding energy that holds the nucleus together. That tiny bit of missing mass packs a real punch. Alright, let's dive deeper into this binding energy. It's calculated using an equation. Binding energy, E, equals the mass defect, dm, times the speed of light squared, c2. To grasp the magnitude of this binding energy, imagine trying to pull apart a helium nucleus which has 2 protons and 2 neutrons. You'd need an incredible amount of energy to overcome that binding force, like trying to rip apart a phone book with your bare hands. When we talk about nuclear reactions like fission or fusion, we're essentially talking about manipulating this binding energy. Chapter 4. The Nuclear Force, a powerful dance of attraction. What exactly is this glue that holds the nucleus together? That's the nuclear force, one of the 4 fundamental forces in the universe. Unlike gravity or electromagnetism, the nuclear force is extremely short-range but incredibly strong. It only kicks in when protons and neutrons are incredibly close together, overcoming the electrostatic repulsion between protons. Imagine 2 magnets with the same poles facing each other. They repel, right? That's like the protons in a nucleus. The nuclear force is like having a tiny invisible hand that forces those magnets together, despite their best efforts to push apart. Chapter 5. Radioactivity, when nuclei go rogue. Sometimes nuclei get a little restless and unstable, leading to radioactivity. Think of it like a hyperactive puppy, bouncing off the walls and causing a ruckus. This ruckus is what we call radioactive decay. It's when an unstable nucleus spontaneously emits particles and energy trying to reach a more stable state. While the word radioactivity might sound scary, it actually plays a vital role in our lives. Techniques like PET scans use radioactive isotopes to create images of our internal organs, helping doctors diagnose and treat diseases. And those smoke detectors in your home? They rely on a tiny amount of americium, a radioactive element, to detect smoke particles. Chapter 6. Nuclear energy, powering our world, atom by atom. At its core, nuclear energy is about harnessing the immense power locked within atomic nuclei. Nuclear power plants use this energy to generate electricity, primarily relying on nuclear fission. In fission, a heavy nucleus, like uranium, is split apart, releasing a tremendous amount of energy in the form of heat. This heat creates steam, which drives turbines, powering generators that produce electricity. It's crucial to recognize that nuclear energy is a carbon-free energy source, meaning it doesn't contribute to greenhouse gas emissions. As we face the challenges of climate change, finding clean and sustainable energy sources is more critical than ever. Chapter 7. Nuclear fission, splitting atoms, releasing energy. Let's take a closer look at nuclear fission, the process that powers nuclear reactors and atomic bombs. We start with a heavy, unstable nucleus, like uranium-235. When this nucleus is struck by a neutron, it absorbs the neutron, becomes highly unstable, and splits apart, releasing a tremendous amount of energy and more neutrons. These newly released neutrons can then go on to strike other uranium nuclei, creating a chain reaction. This chain reaction releases an incredible amount of energy in a very short amount of time. In a nuclear reactor, control rods are used to absorb excess neutrons, ensuring a steady release of energy. Chapter 8, Nuclear Fusion, the Holy Grail of Clean Energy? If nuclear fission is like splitting a heavy atom apart, then nuclear fusion is like fusing light atoms together. It's the process that powers the sun and other stars, and it has the potential to revolutionize energy production here on Earth. In fusion, we're combining isotopes of hydrogen, called deuterium and tritium, to form helium, releasing a massive amount of energy. Achieving nuclear fusion on Earth requires creating conditions of extreme temperature and pressure, similar to the core of the sun. Scientists around the world are working tirelessly to make fusion a reality. Fusion offers several advantages over fission. It produces no long-lived radioactive waste. The fuel source, hydrogen, is abundant, and it has the potential to provide a nearly limitless supply of clean energy. Chapter 9. Thermonuclear Fusion, the Power of the Stars Unleashed. This is the process happening in the heart of stars, where immense temperatures and pressures allow hydrogen nuclei to overcome their electrostatic repulsion and fuse together. This process is responsible for the sun's energy, the light and warmth that sustain life on Earth. But it's also the driving force behind the most powerful weapons ever created, thermonuclear bombs. These weapons utilize a fission bomb to create the extreme temperatures and pressures needed to trigger a fusion reaction. It's a stark reminder that the same forces that power the stars can also be harnessed for devastating purposes. Chapter 10. The Coulomb Barrier, the Nuclear Bouncer. Alright, let's talk about why nuclear fusion is so difficult to achieve here on Earth. This electrostatic repulsion creates what we call the Coulomb Barrier, a kind of invisible energy barrier that prevents nuclei from getting close enough to fuse. Think of it like a tough bouncer guarding a nightclub. Only particles with enough energy can overcome this barrier and get close enough for the nuclear force to kick in and fuse them together. In the sun and other stars, the intense heat and pressure provide the energy needed to overcome the Coulomb barrier. Scientists are exploring various methods such as magnetic confinement fusion and inertial confinement fusion to achieve the temperatures and pressures needed to break through the Coulomb barrier. Outro nuclei, the microscopic powerhouses of the universe. From the energy that powers our sun to the technologies that diagnose diseases, the world of nuclei is full of wonder and potential. We've learned that mass and energy are intertwined, that binding energy holds the nucleus together, and that nuclear reactions can release immense amounts of power. So keep exploring, keep asking questions, and never stop being curious about the world around you. And if you found this video helpful, don't forget to like, share, and subscribe to our channel for more mind-blowing science adventures.